Thank you very much. First of all, let me thank the organizers for invitation and for organizing this nice event. And in comparison to previous talk, which was addressing a general view of quite a wide topic, diamond models, I will here address a very specific quantity, emptiness formation probability, in a very specific model, the square eyes. So sorry for this. And this is joint work with Andrei Pronko from Steklov Mathematical Institute in St. Petersburg. So what I will speak about is a six-vertex model, but at a specific value of its weights. So very fast, I will recall what is a six-vertex model. It's a model of errors on edges with some constraint on possible vertex configurations. So you must have the same number of incoming and outgoing arrow, and so you have only 6 possible vertex configuration, and you assign weights to these 6 configuration. And since I will be interested in fixed boundary condition, I can choose symmetric weights, that is only 3 independent weights, and this makes 2 independent parameters, which are delta and t. T is not really a very important parameter. It's kind of introduce some asymmetry between these 2 weights, but it does not influence so much the physics, the phenomenology of the model, while delta is really a kind of parameter which weights the interaction. You can really see this model as a model of domino tilings, and when delta equals 0, there is an exact correspondence. And indeed, for particular choice of boundary condition, you can even reproduce that ArXiv diamond. But as soon as you tune delta away from 0, you are like putting some interaction between the dimers in such a way that you favor, for instance, configuration of dimers of this kind, rather with respect to this one, let us say. And so things become a little bit more complicated. If you tune your parameter delta to the very specific value of delta equal 1/2 and t equal 1, but this is only partially relevant, what you obtain is a square eyes. That is a 2-dimensional model of eyes. It lives on a square lattice. I did not say that. And in the following, instead of errors, I will use a path description. So you can see this as a model of path, but the path can oscillate. You know, here you can see this as an oscillating point for the path, and you give a weight also to each turn, or vice versa. And since you have only 2 kinds of turn, you see that the paths are director. You can see them as flowing, for instance, from the top to the left. And this model has a very rich history and very rich phenomenology. And this is a phase diagram of the model. So as I told you, for delta equals 0, which is called the free fermion point, the model is kind of determinantal, and you can put it in correspondence with domino tilings. But in general, you have some delta, which varies on this direction. And this phase corresponds to the rough space. It's an extension, a generalization of the rough space that you have in domino tilings or in dimer model. This corresponds to what is called the smooth phase in previous talk, and these are the 2. They correspond to the flat. This will give rise more or less to the facets in the dimer model. So I will specify delta equal 1/2 and t equal 1. So I will leave here. This is known as combinatorial point because it is in bijection with what a very known combinatorial object, which is alternating sign matrices, which has been studied independently by combinatorialists in the last 30 years. So I will choose a particular kind of fixed domain condition, which are called domain wall, in which all the paths enter from the top. So you have an n times n grid, and you have n paths, so you completely fill the top row, and they go out on the left. Okay, so why we are interested in this? Because this kind of boundary condition, which mimic, in the case delta equals 0, mimic the ArXiv diamond, give rise to limit shapes. And here you really see simulations. This is for delta equal 1/2. And this was generated using a software made by Wieland. It's based on coupling from the path by Prope Wilson. And you can see that indeed you have the separation between disordered and ordered phase, exactly like in the dimer models. But if you look more precisely, you will see some small difference. Here red is a guide for the I. It is a circle, the Arctic circle of domino tiling of Isaac diamond. But when you vary delta, the real Arctic curve is the blue line, which is slightly different and which varies depending on delta. This Arctic curve, the explicit expression, analytic expression of this Arctic curve has been around for some time, but it is conjectural. It has been proven only in recent time for the sole delta equal 1/2 case. But the next question you can address then is the fluctuations. You would like to study what are the fluctuations here, and you can probe this fluctuation in many ways, but for the two main ways, one is you imagine to live on this diagonal, and you can look at the intersection between the most external path and the diagonal, and you will see this point, which according to the sample you are considering, fluctuates, and you are interested in the law governing these fluctuations. You can also consider a slightly different statistics in which you look instead in the neighborhood of the intersection with the diagonal, you look at the maximum of the most external path. These two different statistics are both interesting, and they are, at least in the dimer models, they were both observed and they both studied and put in correspondence between the GUE and the GOE Tracy Widom distribution, which arise naturally in random matrix. And indeed, it was even proven that if you have GUE for the first statistics, the one of the intersection for the diagonal, in the case of the Airy process, then for the second statistic, you will necessarily have GOE. This was proven by Corwin, Casteller, and Remenick. This was for delta equals 0. We are interested here in genic delta, but we are not good enough. We will study the delta equal 1/2 case, and we have some hints that we have still Tracy Widom. There are very recent simulations by Korepin and collaborators and Pronko. Here, this picture is from Pronko. It's at delta equal 1/2 and t equal 1. The black line is just a plot. It's not a best fit. It's a plot of Tracy Widom distribution F2. And if you would plot, for instance, a Gaussian, you will really see something slightly significantly, relevantly different. Here you have, you will just observe a parabola, a symmetric parabola. This is logarithm, you see. And when you make simulation and you increase n, you really see, this has the black point, they collapse very convincingly on the Tracy Widom distribution. And also, we have some more.
Can you clarify what exactly is wrong here? Because probability density will not, is it
no, here you look at the intersection between the diagonal and the most external path for many samples, and then you plot the difference between this and the known Arctic curve for several samples. So you take a sample, you plot this intersection, and the difference with respect, you have some, so let us say the Arctic curve is here, because we are on a line now. Then you plot several samples of this external path, and you will see some distribution.
Okay? So this is just density.
So histogram, just not histogram height.
But then it looks strange, but the histogram is like a semicircle, is it?
No. This, here you have x, where x is the variable of Tracy Widom. Tracy Widom is the probability of having no path between x and infinity.
Oh, I see.
And
So
here
you don't have linear scale.
okay,
This is logarithmic.
Yes, logarithmic is here. So a Gaussian would be just a parabola. Okay? So yes, a more indirect, but anyway, strong hint come from Ayachita Johnson, which very recently proved that the second statistic, the one of the maximal, indeed obey Tracy Widom distribution F1 for Gaussian orthogonal ensemble. So, of course, the theorem by Corwin and collaborators goes in the other direction. If you have GUE for one statistic, you have GOE for the other. This is the reverse, so it's not a theorem, it's just a strong hit. So, we want to say something more about this. Part of what I will say is conjectural, part of what I will say is rigorous. So So let us introduce a few objects. The first object is a partition function. I put just a thick path when you have a thick path on the boundaries. These are fixed. Here I have no path, so I have put a red point. Inside, this means I am summing over all possible edge configuration compatible with the ice rule and the vertex of the six-vertex model. Then, since I am at ice point ABC equal 1, I have only to weight all this configuration with weight 1, and this gives you the partition function. The partition function for generic delta actually was evaluated as an Isergin-Korepin determinant by Isergin and Korepin in the 80s. And it's a very peculiar determinant. You are considering some non-homogeneous models, so the vertex depend on the coordinates. And you can write these determinants. Then you can, if you want to do some statistical mechanics, you are interested in putting all the vertex the same. So you do what is called a homogeneous limit, and what you obtain is some determinant of some matrix of Hankel type. Then another, I have to introduce this quantity because they will play a role in what follows. Another quantity is a 1-pound boundary correlation function. This is, since we have n paths here and 1 is getting out from the first line, if you look at the first row, you will necessarily have 1 and exactly 1 empty edge, which will be at some point, you can ask what is the probability of observing it at position R. And this is called 1-pound boundary correlation. We will denote it in this way. And it was evaluated over 20 years ago. Andrei Pronko was student at that time. It was evaluated that some, again, Isergin-Korepin determinant or Hankel determinant in the homogeneous limit, but with one last row of the matrix modified. So you have an n by n matrix, and you divide by the original Isergin-Korepin determinant, and you have what is this probability. And then you may be interested in doing the asymptotics. And this can be done, actually, and was done. Then the quantity I will be interested in is the emptiness formation probability. So we just fix some point on the lattice. The coordinate goes R in this way and S in this way. And I ask, what is the probability of observing a frozen rectangle here in such a way that its corner is at position R and S? I call this quantity emptiness formation probability. I denote it as this way, depends on these two coordinates, and n is the size of the lattice. And this quantity is quite interesting because you can see that if RS are very close to this corner, you expect to have probability 1, and if RS goes inside, when inside the disordered region and the vertic curve, this will drop to 0. In the asymptotic, in the scaling limit, you expect a stepwise behavior in correspondence of the vertic curve, and so this is a useful quantity to determine the vertic curve, and this is actually how it was done. How it was done? Well, you need to compute this quantity. You can compute it using methods from integrable model, quantum inverse scattering, algebraic Bethe-Ansatz, etc. And what you end up with is some multiple integral representation, MIR, which was provided quite some time ago indeed. And I will now introduce this MIR, which will be the main object of the talk, which is quite complicated. So first, a building block of the MIR is this boundary correlation function, which I have introduced before. You just build this generating function. Since this is a probability, and you are summing over all R when z equal 1, you obviously have Hn of 1 equal 1. Note that this is a polynomial of order n, but the coefficients are determinant, n by n determinant of big matrix. Rather complicated because they are all the same, but with one modified column. Then we build another determinant. Out of this generating function, we build this determinant, which is obviously totally antisymmetric in its variable. You divide by some van der Monde, and what you get is a symmetric polynomial in the S variable Z1 then S, symmetric polynomial degree n minus 1. For expert, I can say that this is an alternative representation with respect to Isergin-Korepin 1. In Isergin-Korepin, you have determinant of some kernel, and here you have the determinant built it's kind of a bootstrap because it's built in terms of boundary correlation function, which is kind of inverse calculus. You express something simple in terms of something more complicated, let us say. So it's not clear why it's useful, but it will be useful. This quantity has been built in such a way that if you put one of the variables to 1, you obtain just the same function with one less variable. If you put one of the variables to 0, again, you obtain the same variable, the same function with one less variable and with the index decreased by 1. And also you obtain an overall coefficient. So this is a main building block of EFP. EFP is a multiple integral, S-fold integral, where S is a vertical size of the frozen rectangle. And you have some measure here with pole in 0 and 1, which can be of relevant order. You have some double product. Numerator is a van der Monde, but denominator has a more complicated structure. And then you have this determinant of determinant I have presented in the previous slide. Actually, many multiple integral representations of this kind that appeared in related model like ARXiv, also six-vertex model, mainly in its stochastic version. What I would say is that in general, the equivalent, the corresponding element in this multiple integral function, which corresponds to this Hn of S, is slightly more explicit. Its null is more explicit usually. Anyway, let's go on. So what I have told till here has been known for years. But what I want to say now is that we have this multiple integral representation, and what can we do through this? Just to see when it is 1 and 0, it's really very heuristic approach that we developed, and it is clear that it is very difficult to build any rigorous asymptotics. So what we want to do is to build some alternative representation as some freedom determinant, and to see if then when we have this freedom determinant, we can use standard tools of asymptotic theory to determine the fluctuation of the Arctic curve. So what I will say in the end applies only to the delta equal 1/2 case, but some of the intermediate tools are valid for generic delta, and I think it is worth to present them in generality. So let us restrict to t equal 1 just for simplicity, but let us deform the integration, make a change of variable from z to 1 over z. So our integration around 0 becomes integration around infinity. And I have rewritten the integrand in this way just for short-time notation. And then what happens, so what we want to do is now to shrink down this contour around the pole 0, 1, and double poles here. So here there is some kind of miracle which appears. It appears that these poles, which would give you complicated contribution, give actually vanishing contribution. Part of these poles are compensated by zeros hidden into this complicated function, and some other of these poles give a finite residue, but this finite residue vanishes when then you integrate around the other contour. So you are left, you can shrink down the contour to 0 and 1, to the union of these two contours, and so you have an S-fold integration of this kind, where J is the same object. Now we can expand this, integrating everything at around 1 or around 0 or a little bit half and half. And this is what I call, define my IK. IK is just the sum of all integrals which have exactly k integration around 0 and S minus k integration around 1. So when you have this, well, for people who have studied the paper by Tracy Widom on ArXiv, you know where we are going towards. Before continuing, I will present you two very simple lemmas. The first one says that if I integrate, if here I take I0, that is I integrate only around, I take everywhere the circuit around 1, the result is very simple, it is just 1. And why it is this? It's very simple to see. So here, when let us do the integral starting from Zs. Zs is power 1, so it is a simple pole. We have just to replace 1 everywhere, and when you replace 1, this becomes just hn s minus 1 with one less variable, and here this factor compensates nicely, and you obtain exactly the same integral and integrand with one variable less, and you can iterate, and in the end you just obtain 1. The same when you consider around 0, and so we have this second lemma. Here the situation is slightly more complicated. We obtain the product of the value of hn, hn minus 1, hn minus s plus 1. I will not put the argument 0 from now on for simplicity, because the formula will become very soon quite heavy. So when there is no variable here, this means just that z has been set to 0. Okay? So we have these two lemmas, but what can we say when instead we want to consider ik, where k is different from 0 and s? So k integration are around 1, well, and s minus k around 0, vice versa, sorry, k around 0, blah, blah, blah. I recall you that we have this function, and so when you will compute this, you will obtain some quite complicated formula already for s equal 2. When you take one contour around 0 and one around 1, it becomes a bit heavy to do by hand. You can do it, but it's several pages of calculation, and what you obtain, you have to take into account that here you have this function hn, which appears as a product in this determinant, which is companion with shifted indices, and then they will be evaluated at some, the residue will be evaluated at some pole, which can be of high order. So what you will have is appearance of high derivative of various order of this function h, evaluated at 0 and 1. So,
sorry, are you using k in two different contexts here?
No, I think there is a typo there. Sorry, you are saying. Right. No, yes, let us call it L. Okay, sorry.
The second k on the last product there.
Yes, here, nothing to do, yes. Okay, so we will have, we want to see if we can guess some structure in this ik, and so we have to reduce the number of formally independent objects to as little as possible. And so we need some relation to express, for instance, hn third derivative with n shifted by 2 units, evaluated at 1, in terms of other similar quantities to reduce everything evaluated, for instance, at 0. So for this, we need some identities. I will show you some identities here. They are quite, well, they are easy to compute indeed, in principle, in the sense that in the year we have accumulated various independent and different multiple integral representation for EFP. And so you can compute them for the same values, and you will obtain relation between this equality of multiple integral representation will give you identities between the function h evaluated at 0 and 1. But it is not possible, I mean, you can build them recursively, but it's not very easy if I say, please build the fifth one, I am not able. Mathematica is essential here. So these are valid for any delta t, but we will use delta equal 1/2 later on. And as I said, yes, you can compute them in this way, and they allow to express hn of 1 and its derivative in terms of hn of 0 and its derivative, so that you will have less independent object. Then we have a second set of derivative. This second set, unfortunately, holds only at delta equal, oh, sorry, I forgot to say something here, important. This second lemma is valid only when R is equal to n minus s. This means that you are asking for a square and not a rectangle to be frozen. So you are only, when you will move this s, you will be always, the corner will always stay on the diagonal of the lattice. okay? And the second limitation is that delta must be 1/2, otherwise we don't know what to do. And here it's the same, again, the second set of identities, unfortunately, also only for delta equal 1/2, so we are unable to, at the present time, to extend our results to generic delta. So this follows from the fact that when delta equal 1/2, you have alternating sign matrix. This has been studied in detail. In particular, the refined enumeration of alternating sign matrix has been worked out by Zalberger, and you can, when you build the corresponding generating function, it's just an hypergeometric. And exactly, this refined enumeration is nothing else than the boundary correlation function for the six-vertex model. So we have this kind of identities which you can derive using all the overwhelming quantities of identity for hypergeometric function. Again, they relate derivative of n, of hn of n evaluated at 0 in terms of lower order derivative. And the two sets allow us to express the result of our integration in a smaller number of variables. So what we want to do, because we want to follow Tracy Widom and to expand our multiple integral in terms of this quantity I k that I have introduced earlier, and to see if I can rewrite this as a determinant of some S by S matrix, where here lambda is just a formal parameter. And so our aim is to see if we can rewrite an S-fold integral, quite complicated, as a determinant of some S-fold matrix, which is of freedom type, in the sense that if you have this kind of determinant, you can expect to transform it in some other determinant of freedom time for some linear integral operator. So when S equals 0, we know that this is 1. When S equals 1, it's known from the expansion of determinant of 1 plus something that the last term will be just the determinant of A. So we know from our second lemma what is the determinant of this matrix now. But we have to rebuild all of it. So in what follows, we will observe this kind of symmetry, that when you study the case S equals S, you can eliminate the last row and last column. You are left with a block of size S minus 1 times S minus 1. And this is closely related to the solution of the problem when S is one integral less, is S minus 1 actually. So this allows you to build this matrix A recursively. What you have to do is just a formal shift in the variable S and N. And also, A start to become quite complicated after a few values, and so we resort to this factorization, which is slightly different from standard. We have first the diagonal, then lower triangular and upper triangular. And also, now what I will have to do is try to solve this equation for the various power of trace of A and to determine A. So it's a kind of Sudoku. And we have to simplify the symbol we are using. We can forget about the meaning of this symbol. We just have some symbol, which we call bi, which has the value at 0 of the function, and k prime I, which is essentially the derivative k second of the function, always evaluated at 0. But forget, they are just simple, and we want to solve some Sudoku. Case S equal 1. In this case, the integral, you write it is very simple. You can do it in one line. You have a pole at 0, a pole at 1, and so you obtain this quantity. And using our alphabet to reduce complicancy of symbols, we rewrite it this way, which we already knew actually from our two lemmas of a few slides ago. And we are now looking for a matrix A such that the determinant 1 by 1 a matrix A such that its determinant is 1 minus B0. So the solution is obvious. Okay? So let us go to S equal 2. For S equal 2, you have to compute the integral. It starts to be a little more complicated. The first one is 1 and should be equal to 1. It's fine. The second one should be equal to the trace of A minus. And the third one should be the determinant of A. So we have two conditions. But of course, A is determined up to similarity transform because we are looking at its determinant. So we don't need and are unable actually from this condition to determine the full matrix A. So here we have as appearance of Hn minus 1 evaluated at 1. So we want to simplify a little bit this expression. We use the first set of identity, and we get this simplified answer. Then it's just a Sudoku. We observe that when you put B0 equals 0, you obtain the expression of previous page. You see, 1 minus B0. Here now you have 1 minus B1. So what you would like is that when you truncate this matrix to here you should have the B1, according to the symmetry, the ansatz I have explained to you before. Then you impose these two conditions, and you are done. Up to similarity transform, and of course you see that the determinant is B1, B0 as it should, and this is your expression. Okay, this is not enough to guess any structure yet, so let us go to S equal 3. Here it's really become quite of a big work. So we have to impose all these conditions. And we have already used a set of identity of type 1. And again, if you put B0 equals 0, you see that you obtain the structure of the case S equal 2, so you can rebuild the D, L, and U using the structure of the previous page. You can say check, apart from the fact that you have shifted indices by 1, okay? And then you have to fill the rest of the matrix. And how do you fill this? You impose these three conditions. When you do this, you realize that you are not able to do this exactly. You have some unwanted terms that you don't like and you want to cancel out. And it appears that one of the identity of the second set says that this quantity is 0, and then you are done. Indeed, you have canceled out the unwanted term. I am running out of time. S equals 4, I spare you the calculation, but just observe that the 3x3 block has been built according to our ansatz from the knowledge of previous case, and then you just have to work about it. We are unable to go beyond, so we must recognize some structure already here, or otherwise we are dead. So, well, let us look at these red entries. These red entries, if you look a little bit in the table, are just Laguerre polynomial. You see, look at this column, 1, x minus 1, x squared over 2 minus 2x prime plus 1, etc. Up to a sign, they are just Laguerre polynomial. But the other one are not. Let us look at the other one. The other one, the blue one, if you work, you have some good reason to believe in Laguerre polynomial, and we have some good reason, I will explain you in one slide. Then you look for associated Laguerre polynomial, and you see that the correct combination to choose are this one. So this is quite convincing check, but of course it's still until, so we have, I think that we have proved that this structure is correct for S equal 1, 2, 3, 4, okay, but not more. And then this is not completely symmetric. On one hand, we have two Laguerre polynomial. For the red one, we have only one Laguerre polynomial, but you use Laguerre polynomial identity, and you can write the red one as a difference of two associated polynomial instead of as a sum instead of the difference of exactly the same Laguerre polynomial. Okay? So, what we do? We try to extend this to S equal 5. And in general, to generic case, and so this is a conjecture. So you see, we have a Laguerre polynomial associated with derivative acting on this function h, evaluated at 0. The r is equal to n minus s identically. So n and s are hidden here. I write r for shorthand. And you have this structure. Why do we believe in Laguerre polynomial? Because there is a nice identity. When you have the residue of some function with some factor 1 minus z to some power and some factor z to some other power, you can express this in this way. And since in our integral formula, we had actually function h multiplied by z minus 1, z plus 1, z, the appearance of this Laguerre polynomial in this structure with insight is more or less okay. So I would like to discuss a little bit this conjecture, a little bit more, to be a little bit more clear, more explicit. So what we have is this multiple integral representation, which is rigorous, but very difficult to analyze from the point of view of asymptotics. And our claim is that for any finite S, You can write this as a determinant of 1 minus A, where A is this matrix which I have shown you before. I have just used the Laguerre polynomial integral identity in the reverse way to rewrite it as this way. Okay, as a double integral around 0 of some kernel, this function Ej of Z and W are explicit. So, for people who have some experience in random matrix, well, in random matrix you have some multiple integral, S-fold integral, and you want to re-express it as some determinant. And what you do, you just play with the van der Monde, push the integral inside, and you are able to rewrite your multiple integral as some gram determinant associated to some measure, which is exactly the same measure as the random matrix model. And so you have rewritten your multiple integral as a determinant of some matrix of size S times S, which entries containing a single integral. Here we are not able to do this for many reasons due to the complicancy of the object, but we have been able, conjecturally, we have been able to rewrite it as a double integral. You have this denominator, etc., etc. So the last 7 minutes of the talk will be devoted to the asymptotic analysis of this quantity, which is straightforward. I mean, what I have done, I have studied in detail Johansson's paper, and I have done essentially the same. So, just before going on, let me recall that crucial in this derivation were two sets of identity, and also the ansatz which allow it to build a matrix of size S from matrix of size S minus 1. And yes, we have tried a lot to prove this result, but we have not been able. So this is open problem. Before going on, you could ask, but what about S equal 5? S equal 5, we are not able to compute explicitly the integral, but we can compute them numerically with, exactly with mathematics, I mean. So we did it for S equal 5 and N equals 7, 13. So, because, you know, one could say, well, you have been lucky, you have fitted some condition, but this was an underdetermined problem, you have many solutions, and when you go to S equal 5, what will happen? But so we went to S equal 5, we compute numerically, and these are the result. Of course, when N is smaller than 10, this is 0, because we have no available configuration if the frozen square is half of the lattice. And so these numbers are essentially, so the denominator essentially is the number of ASM, for instance, for a 13 by 13 lattice, and the numerator of the number of ASM on a 13 by 13 lattice with a frozen square 5 by 5. By frozen means with only zeros in the top left square of size 5. And just a note, to compute, for instance, this last one, which was the most difficult, here, when you compute the Fredholm determinant, it takes about 2-3 minutes. When you compute this, it takes 2-3 days on my desktop. So we have really, mathematics at least, find really a nice gain in algorithmic complexity with this new thing, and I hope that human as well. So we have 10 minutes I have. How much time I have? Okay, so I am in plenty of time. So the conjecture says that our matrix Aij has this form. And that you, of course, the function E here depends on S and on N, the two parameters of the model, since we are living on the diagonal. And well, you can, of course, integrate this out, and you obtain now an integral between 0 and infinity of this quantity. And what you have, I mean, the limitation you have, of course, is this. But apart from this, now you have this new expression for the kernel, and then you can trade this index I and j with the index, the continuous index t, to transform a finite determinant into a Fredholm determinant of some kernel of some linear integral operator, which is done in this way. You see, you just sum over the ij which were here, you do the trace here, and you separate the value of t. You split it between the contribution with z minus 1 and w1 1. It is clear that when you take the trace of any power of this object or of any power of this object, the trace will be the same. And so the Fredholm determinant of the second object is equal to the S by S determinant, the determinant of the S by S matrix of the conjecture. For expert, let's just notice that this integral kernel is not of integrable form in the sense of its collaborator. But this is a big problem if you want to compute a systematic asymptotics using Riemann-Hilbert problem, etc. But if you want to compute only the leading order, it's not really a big problem, as you will see, or as you already know. So to do the scaling limit, what we do? We are on the square, so R is equal to n minus S. We introduce some scaling variable y, which is essentially the ratio between S, the size of the frozen square of the emptiness formation, and the size of the lattice. And S lives in 0, 1/2, because after this, it's just everything vanishes. And just to recall, sorry? This is probably dead. Maybe I moved something. It's on. Okay. Sorry for suspense. So just to recall the notation, so y is this variable from 0 to 1/2. It lives on the diagonal. This is the arctic curve which was evaluated by us and then confirmed rigorously by Amol Agarwal. And it is not a circle. It is an arc of ellipse. You know that when delta is not anymore 0, here we have some analytic function. We have some breaking of analyticity. And so this is just arc of the curve, which is replicated by symmetry 4 times. And here we have some discontinuity in the second derivative. And there is a value when y corresponds to the frozen square touching the arctic curve, which is this y equal yc. Okay? Now let us come back to our kernel and make some scaling analysis. So we just replace expression for E. We make all the study of the asymptotic expansion of all the functions which enter it. We collect all terms. And we end with some pieces which were already known, already there. Here is the part which depends on N and S. And here is some part which depends on Z and W in complicated way, which is explicit, but I write just F for shorthand. And does not depend on N and S. So this is a function which will be interesting in the saddle point approximation. You rewrite it in this way, and you study its saddle points. You have 2 saddle points. The 2 saddle points have this expression, and you see that the 2 saddle points can be both real, both imaginary and complex conjugated, or coincide. The case in which they coincide correspond to y equal yc, where yc is exactly when you are touching the arctic curve. So this is a sign that our conjecture is at least reproducing the correct intersection between the arctic curve and the diagonal. And if you perform the saddle point approximation and you replace everything, you see that when you are in the frozen region outside the arctic curve, you have 2 real saddle point solution. You have the important one is closest to the origin, and it will give you some exponential decay. Vice versa, if y is larger than yc, you have 2 imaginary complex conjugate saddle point, and they are both relevant, and the combination gives you some oscillating behavior. And this phenomenology exactly reproduces what is known for Daimer model from this celebrated paper. So you have to deform the contour. So I rewrite this. You have to make some expansion. You have to be careful. Actually, we rewrite y in the vicinity of the critical point, in vicinity of the arctic curve. So eta is some small parameter. Actually, if you do a careful analysis, you see that eta is for the n to the minus 2/3. And this is for the n minus 3rd. This is slightly sloppy, but it's correct if you identify lambda square with eta. And then you have to deform the contour. Initially, it was, if you remember, in the kernel, you have this double integration over C0. We deform the contour in this way when this is very similar to airy contours. You see, this is 2 pi over 3. And you go, the contribution from the saddle points come, of course, as usual, from the vicinity of this point. And then you have a second integral for the variable z instead of w, and this will give you exactly the same for mu instead of lambda. Okay, so you do some scaling. The scaling is very standard again. And when you scale the variable and the kernel, you obtain this new kernel where gamma tilde is thus the rescaling to infinity of this contour gamma which live inside this small circle. Okay? So gamma tilde becomes actually modulo assign it is essentially airy contours. And when, so let us summarize what we have obtained until here. So this is a factor, it's not conjectural. We have some matrix, which was given in our conjecture, but let us forget it's related to EFP. It is a matrix which is defined. You can study this matrix in the scaling limit in the vicinity of the double saddle point and with correct rescaling, and you observe that it is equal to the determinant of some Fredholm determinant, to the Fredholm determinant of some linear integral operator, K, with this kernel. Okay? Well, then you are done. This kernel, it's very easy to see that it is actually coincide with airy kernel. Again, you use you play with the integral to move the trace, and what you can prove is that this freedom determinant with this kernel is equal to the freedom determinant of airy kernel, which is, I would say by the definition almost, GUE this Tracy Widom distribution from random matrix model. So we are done. So to conclude, what I have shown you is first a conjecture which offer you a new expression for EFP, which is conjectural, but which is very, very simple. And second, it's a theorem that this matrix, this determinant of 1 minus a in the scaling limit and in the vicinity of the arctic curve behave as a GUE Tracy Widom distribution. So just to say that these coefficients are in complete agreement with the one obtained by G through an exact analysis of another statistic obtaining GOA in the paper by Ayachita and Johansson. And also, these numbers are in complete agreement with numerics. So, thank you.